This is Geometry, Chapter 10, Lesson 3. But before I start Lesson 3, I want to go back and look at some ratios, because to go forward, we need to just look back. And we have already discussed the fact that similar polygons, their sides are proportionally related, and that there's some scale factor that we can multiply one by to get to the other. And it's really just a dilation, right? All the angles are equal, but the sides have been dilated. The angles have not been changed, all right? But I want to work through, and I really want to settle in on this geometric mean and how to write proportions. So, ratios can be written as fractions, or a ratio can be written, that's 6 to 15. That's 4 to 10. Okay, so ratios can look like that. Ratios can look like this. Now, how can I decide if these are equivalent ratios? Remember, when I have a fraction equaling a fraction, a ratio equaling a ratio, I'm always going to use cross multiplication. I can cross multiply to see if these ratios are in fact equivalent. So remember, my equal sign always stays in the middle. 6 times 10 is 60. 4 times 50 is 16. Are these equivalent ratios? They in fact are. All right, so you can look at a ratio that way, or I can be given four numbers. If I just gave you 4 numbers, 30, 6, 5, and 1, could we write equivalent ratios? Well, I look to see which products equal, and that's going to be my extremes and my means. I know 30 times 1 is 30. So I want them to be crisscross, right? I know 6 times 5 is also 30. So I want to multiply them that way. So I could write it like this, or I could write it 6 over 30 equals 1 over 5. As long as I know, I'm looking at the products to see if the products are equivalent. All right, what if I gave you these 4 numbers? So you're really getting this extremes and means. 3, 10, 15, and 2. I'm looking at products. I know 3 times 10 is 30. I know 2 times 15 is 30. These have to be my extremes. These have to be my means, or vice versa. And then these have to be my means. Okay? All right, now, geometric mean. Remember, the geometric mean, I'm going to write it like that, is equal to the square root of the product of the extremes. Extreme times extreme. What if I just asked you, what is the geometric mean between 10 and 40? Then you would, that is your extremes. The geometric mean would be the square root of 10 times 40, which is the square root of 400, which would be 20. Wait, is 20 times 20? No, that's not it. It will be the square root of 400, which is equal to the square root of 4 times 100. That's the same thing. Okay, so this is some algebra review. All right, you see how I broke this down? Perfect squares. That's the square root of 4 times the square root of 100. So that's 2 times 10. That would be 20. So it is 20. All right, so you can logically think through that. And so I could give you any two numbers and ask you the geometric mean. And it's just the square root of those values. All right, now let's look at side splitter theorem. I don't want to differentiate this from the mid-segment theorem. With the mid-segment theorem, the mid-segment, we had triangle, this side bisected, that line, that mid-segment, this was your mid-segment. It bisected both of the sides. It was half, I'm just going to label that X, label that Y. It was half the length of that third side, and it was parallel to it. Okay, that's the mid-segment theorem, and we use that in our proofs. The side splitter theorem is different. It's these proportions, it's these ratios that we're going to use. The side splitter theorem simply says I'm drawing a line inside a polygon at any point, but it'll be parallel to the third side. It does not, here's the difference. It does not necessarily bisect the sides. It is simply parallel to the third side. So we cannot use the mid-segment theorem. It's not always, this line is not going to be half the length of that third side. The side splitter theorem, this is the side splitter theorem. It says if I have a polygon and at any point I draw a line parallel to one of the lines, then there's something that I could know about this. So we have to go back to our parallel lines. I'm just going to label these sides A, B, C, D. I can prove to you that this little triangle at the top, I'm going to label the angles A, B, C, and I'll label these angles D and E. All right. Because I have parallel lines, I know that this angle B equals that angle D. Because here's your parallel lines, that is your transversals. Angle B and D are corresponding angles, and parallel lines form equal corresponding angles. I can also say that angle C equals angle E for that exact same reason. And I can say that that angle A, it's both in triangle ADE and it's in triangle ABC. So now we have all three angles of a triangle are congruent, of those two triangles are congruent. So ADE is actually similar to ABC, the whole triangle. So their sides are going to be proportionate. They're going to be in the same proportion. So I could say lowercase a over lowercase b is going to equal the ratio of C over D. All right, I'm going to label these X and Y because X and Y are also the same proportion. So A over X, that's in this small triangle, A over X, and I have to write the corresponding sides in this proportion when I'm writing the proportion, right? So that A over C, it's B over D, so it divides it proportionally. I can also, we're going to work through some examples. It's just helpful to work through some examples that are not in your textbook, all right? I could say A over X is the same as C because C corresponds to the A side. What corresponds to the X in the big one? Y. Okay, so I have lots of examples to work through. We'll work through some of the easier ones first. Okay, here we go. Side splitter theorem divides those sides proportionately. All right, so if I have a triangle. And I say those two sides are parallel. And I label them 6, X, 3, and 4. I know that those parallel lines divide those sides proportionately, and I can solve for the unknown side by writing a proportion. 6 over X equals. Then I have to go to the other side. What side corresponds to 6 is the 3 over 4. And then I cross multiply to solve because I have a ratio equaling a ratio. And it's 3x is 24. I divide both sides by 3. Here's your algebra, right? X is equal to 8. All right, so it divides those sides proportionately. All right, let's do another one. Looks a little different. Those two sides are parallel. Here, I'm given this side, okay? All right, so I'm going to take 6 over X in the small one. But now I'm going to look in the big one. Well, I know that X corresponds to 16 in the big one. It's the same side. But what side corresponds to 6 in the big one is this entire side. Not just the 12, it's the entire side, okay? If we were going side to side, we could do 6 over 12 equals this over that. But because I'm doing the small one to the whole one, because this is in the entire base of that triangle, I have to do the entire side. So that's 18. And then I cross multiply. 18x equals 6 times 6 is 36. That's 96. I divide by 18. 96 divided by 18. I never need a calculator in this class, but I'm going to do it here. 96 divided by 18. That's 5 1/3. So x equals 5 1/3. It's actually 5.333. But it's 5 1/3. Okay, so that's kind of an unusual answer. All right, let's look at it. Let's look at another one. I have several. Okay, so you have to decide. If I'm going just the sides, I can do side, piece over piece. But when I'm looking at the base, I have to look at the whole, the small triangle and the whole triangle. All right, let's look at another one. This one's a little difficult as well. Might look like a right triangle, but don't assume that it is. All right, now my ratio is going to be the piece over the whole equals that piece over the whole. So it's going to be 6 over, I have to add those two, x plus 6, right? The entire length is x plus 6 equals the piece 8 over the entire length 20. All right, you probably can't see that, huh? Very well. All right, again, I cross multiply. 6 times 20 is 120. When I cross multiply here, it's 8 times x plus 6, and I have to distribute that 8. So it's 8x plus 48 equals 120. Now's your algebra. I'm subtracting 48 from both sides. So I have 120 minus 48. I believe it's 72. But let's just make sure. It is, in fact, 72. 8x is 72. Now I divide both sides by 8. The value of x is 9. 72 divided by 8 is 9. Okay, we're going to do a couple more. It's all side splitter theorem. 3. The whole length here is x. This is 4 and 8. But I need the whole length, which is 12. Because I'm going to go this length over the whole equals this length over the whole. So it's going to be 4 over 12 equals, the piece that corresponds to 4 is that 3. The piece that corresponds to the whole is x. All right, so then I cross multiply. 4x equals 36. I divide by 4. The value of x is 9. All because of that side splitter thing, because when we have the side splitter, it forms equal corresponding angles. So then I can use proportions to solve. All right, let's do one more. 12, 15, x, 8.75. Now, because I just have the two sides, I'm just going to do 12 over 15 equals x over 8.75. And I'm going to cross multiply. I know that's 15x. 12 times 8.75 is 105. When I divide both sides by 15, the value of x is 7. Okay, so I can use the side splitter theorem to calculate these sides, because it forms similar triangles so that all of these sides are proportionate.